Thank you. Hi, my name is Ramkumar, and I work for post-sale support in NSO. I'll talk about the basic NSO architecture here, as Jan just said, and this will be the agenda for today. So I'll just briefly touch upon what network orchestration is. I think I don't have to sell what is NSO or network orchestration or what is network automation is to you guys, because you're already sold on NSO, I believe. Um, and then I'll go about the basic architecture of NSO, and I'll talk a little bit about the building blocks of NSO, which are sort of the very basics to, the components which make NSO so powerful. And then I'll talk about use cases of NSO, how people are using it, and what are the possible configurations that you can use NSO in. Network orchestration, as you all know, it's a roadmap of getting to end-to-end management of the whole network. So from configuration to policies, to automating the services and provisioning and everything. So Wikipedia defines it as automated arrangement of coordination, and management of network components. So you should be able to provision the services on demand, and you should be able to manage the lifecycle end-to-end completely using software and automating as much as possible without too much manual intervention. That's the idea of network orchestration or software-defined networking in general. And NSO is one of the core components that we position for doing this orchestration. And continuing, I'll now talk about the logical architecture of NSO. So this is the basic architecture diagram of NSO. So going in, on the top, you have OSS systems or order management systems and so on. And then you have multiple components here that I'll go into in a little bit. And down towards the south, you have the actual devices. And they can be actual physical devices or virtual devices, or they can be other NSO instances as well. They can be used for, you can use NSO to directly touch devices and manage the config, or you can use NSO to operate a cloud-based system and spin up virtual instances, and then manage those. A lot of different configurations and use cases are possible. And now, going through each component in turn, the first thing is packages. Packages provide you a way to reuse and basically use your software components in a model-driven way. I'll talk about Yang models later, but in NSO, the whole NSO itself is modeled in Yang, and you write your packages also in Yang. And this gives you a model-driven API to your services. So once you know the Yang model and their capabilities, you'll know what the whole service is capable of and how you can talk to the devices, basically. And then, so a package is nothing but a collection of models and some code. And in some cases, you have some templates as well that tell you exactly what to do. And the behavior and the capabilities are modeled by the Yang models. And then the actual behavior is implemented in software or in templates. So we have APIs in Java or Python, Erlang, and also in C that you can use to implement the APIs that you define in Yang. So the power of packages is that it gives you a way to automate upgrading and provisioning new services. So when your service changes, or when you update your service model or your package implementation, you just put the new package and do a package reload, and then now you have the new software in your system, and you can use that to provision new services or provision the services in a different way. And these are all without any downtime, so you don't have to stop NSO to change your services or service models. That's a big plus. So you can, in runtime, change your change the behavior of your system and upgrade your services, and so on. And the next important component is the CDB. It originally stood for configuration database, but now we don't store only config data here. We store all sorts of state data, alarms, notifications, plans, and so on. So we don't call it configuration database now. It's just CDB. It's a data store, basically. It's NSO's data store. It's transactional and hierarchical. I'll talk more about what is a transaction and what transactional means. It's a hierarchical store in the sense of similar to like an XML database. So Yang is basically hierarchical. So when you instantiate Yang with some data models or with data, it's a tree-like hierarchy, and it has equivalent representation in XML. So it is like an XML database. Of course, it's not exactly an XML database because the internal representation that we use is not exactly XML, but you can think of it as similar to XML. So this is the database that we use to store all the config data and state data. And it's also the central driving engine behind all the other components. It's the transactionality that's the main power of NSO. And the next component is these device and service managers. So a device manager is the component that talks to the southbound devices. So it manages handling of sessions, maintains session pools towards devices, and connects to the device as needed. Actually, it doesn't talk to the, for some type of devices, the device manager talks to the NED, which I'll come to later, and the NED talks to the device. And for some other type of devices, especially netcom devices, there is no code needed to talk in between. So the device manager can directly talk to the device if it's a netcom device. But yeah, so the device manager basically manages connections towards the devices and configuration of the devices itself. And the service manager is, of course, managing services. Services are kind of an abstraction of your service, your network service, like a VPN or a firewall. So you write a service model and some code to do the service to device mapping, or maybe a template to do the mapping. And the service manager makes sure that your service is in sync with the devices. And it's the service manager that actually calculates the net service to device mapping. So these are the other components in the NSO. And next one is one of the more critical components, which is called the NEDs. They stand for network element drivers. They are the ones that are actually managing to talk to the different devices. So it's basically, they're usually implemented in Java mostly, but it's not, that's mostly due to legacy reasons. There's nothing specific to Java in implementing NEDs. And there are different types of NEDs based on the type of the device. So if the device talks CLI, you can write a CLI NED. Or if it's a netconf device, it's a netconf NED, and so on. Cisco itself develops and provides support for a lot of NEDs. For example, Cisco's own devices, or Arista, or all the other type of devices that talk CLI. We have a lot of NEDs that talk to different devices from different vendors. And for netconf, it's usually only the data models, because NSO itself talks netconf natively. So there is no need for any other code between NSO and the device in the net. So if it's a netconf device, you can just take the models from the device and compile it into a netconf net yourself. We do have a Juno's netconf net for talking to Juno's devices. But other than that, if a device speaks netconf, you can just take the models from the device and build your own NED to talk to that device from NSO. And there's also a generic NED. We also have documentation for building a generic NED in our user guides. Using that, you can just a NED is basically a set of APIs that you have to implement some callbacks. Using that, you can build a generic NED to talk to any kind of device, like using a REST endpoint or any other kind of access method. So a NED is basically, it exposes a transactional interface to the devices from the service. So from your service, you don't have to care about what type of device it is or what access method it is using. You can just write your service to device mapping in your service code, and the actual connection and the configuration of the device is taken care of by the NED. Yep.
So the NED is something that is going to help me to talk softbound.
Yep.
Right, with the devices. But is there, I don't know, any kind of way or NED that helps me to integrate with NMS systems? So supposing that I have a service provider,
Mm-hmm.
a lot of different vendors, different NMS systems.
Okay.
So I need to integrate with all of them with the same purpose. Is there any standardized way to make that communication?
So you mean northbound, north of NSO?
Yeah.
No, there is no standard way to do that. I mean, the standard way would be to write a service that is agnostic towards the NMS, I would say. But yeah, maybe it's not very easy to generalize the northbound requirements, I would say. But yeah, we don't have anything like that right now. Yeah, so these are the building blocks of NSO, or the basic architecture. And now I'll talk about what makes NSO so powerful, or the very basic components of NSO. And the first thing is transactions. So this is from some basic computer science. So what is a transaction is, if something satisfies these 4 criteria, it's transactional behavior. So the first is atomicity. So what that means is a transaction is all or nothing. So either the whole thing completes fully or nothing is done, nothing is changed. And that's the first first criteria. And the second one is consistency. So when a transaction is complete, you can say that the system is in a valid state right now. And when another transaction completes, after the transaction is complete, the state will be valid after the transaction. And the validity is defined according to the transaction system. In this case, it's defined by the Yang models and some constraints that you place in the model using must statements or your own validation points. So in NSO's case, what it means is that the CDB is always consistent with the models. And the next one is isolation. So if you have multiple transactions in parallel, it doesn't matter what order they are run. And after all of them are complete, it is as if the transactions are executed in some sequential order. It doesn't matter exactly what order it is. But if you execute all of them in some order, it will be the equivalent to if they are executed all at once. Basically, in NSO, this is guaranteed by locking. So when there are multiple transactions in parallel, the critical region when the writes to CDB happen or done in logged state, so only one transaction can write to the CDB at any point. And then the last one is durability. This means that when something is written to the database, it should be persistent. Sudden power failures or voltage spikes or whatever failure should not affect the data already in the CDB or already in the database. So if you bring up the system again and read the same data, it should be the same as you had before the failure. So, yep. Yeah, so you can change the models in runtime, but then you have to do the upgrading also. I mean, CDB supports upgrading certain types of changes automatically, and if CDB cannot do the upgrade automatically, then we provide a way to hook your own callback to do the modification. So you can read the old data and write the new data in based on whatever changes your model has changed. Um, it's not a service, but we have an upgrade component. We have a API called the Management Agent API that we use to write to the CDB. So when your model is changing and when you boot NSO with the new models, you get the chance to run an upgrade component from your packages, whether it's a Python package or a Java package. You'll be invoked with an upgrade callback within the upgrade component. And in that callback, you can read the data from the old schema and write it to the new schema. That's how you upgrade the database. Well, no, I mean, let's say you have a package uploaded, and then you um, change the data model and then build a new package or new version of the same package, and then you do package reload. When you're reloading, the upgrade component will be run, and you can, yeah, no, yeah, yeah. So that's not in place right now. So there are upgrade systems like something called blue-green upgrade in Cloud Foundry or something, where when you change the package, they offer two ways to the requests. So you can only upgrade part of the load. I mean, you can upgrade one instance and direct the part of the incoming request to the new load, but the remaining part to the old one. And then once you are fully confident, you can migrate it. But in NSO, there is that capability is not yet there. So I mean, yeah, it's not 100% zero downtime, but it's easy to upgrade. And especially when we talk about HA later, I'll say that if you want to upgrade it, you have a master slave config, and your active request will be received by the master. And when you want to upgrade, you switch over to the slave and upgrade the master first, and then bring back the request to the master and upgrade the slave. So something like that. Yeah. So mhm. Yeah, so in our user guide, you can see what are the exact cases that are handled automatically by CDB and what cases require manual intervention. So in this case, when you add new elements to the Yang, it's just new elements are added to the schema, but nothing needs to be done to the data in the CDB because the data in CDB will still correspond to or will still be valid according to the new model. But if you delete something, that's equivalent to just dropping those data from CDB. If you don't manually intervene, then CDB will just drop the data that is deleted from the model. And there are much more complex scenarios where if you change the keys of the list, if you add a new key to the list, that's not automatically handled because you cannot have a value for the new key. And if you change the order of the keys, some of them is handled automatically, but some of them are not. And if you change the type of a leaf, again, some of them is handled automatically because changing a type is just how it's done internally is let's say you have a leaf of type integer or uint 8-bit integers, and then you change it to a 16-bit integer. That's a valid change because you go from 8 bits to 16 bits, so you can just preserve the value that's already there. But if you go from 16-bit integer to 8-bit integer, that's not automatically possible to convert because it will be truncated, some of the values. So then it needs manual intervention. So you can look at the user guide to see exactly what cases are automatically handled and what are not. Okay. Yeah. So these are the requirements for a transaction. And why transactions are helpful is that they help you maintain the state of a system in a consistent way. So if you have transactions and if you have a long chain of events to be followed, if the whole chain is transactional, you don't have to care about failures in the middle. So you start something in one end, and it will either fully complete through the chain or nothing will go. In the ideal case, of course, there are some caveats here and there, but the aim is that if you have a transactional system, it's very easy to provision new services and um, be correct about your services and confident about your services. And if there is a failure in the middle, everything will be rolled back, and you will be in the same state as the prior to your transaction was started. So this is the very powerful building block of NSO that enables you to layer on top of this and build much more powerful constructs. And the next one I'll talk about is reference counting. Sorry. So reference counting is quite an old technique actually. It's used, it's familiar from garbage collection in high-level languages nowadays. Python uses it, and C++ has an option to use reference counting for garbage collection. So what that means is every new object created will get a reference, and if the number of references to an object is 0, that means that that object is not reachable, so that can be garbage collected now. That's the basic idea, and how it is used in NSO is NSO's central algorithm is called fastmap, which I'll talk about later, and that uses this reference counting to ensure that multiple services touching the same data don't remove them when one of them is removed. So let's say that there are 3 services, and each of them touches the same node in the data tree, device tree. When one of those services is removed, you don't want to remove the corresponding element in the device tree, because let's say the services have some common configuration and also some distinct configuration, each to its own. So multiple services can touch the same common config. So those common config will be reference counted, meaning that if 3 services touch the same config, the reference count will be 3. Or if it's already existing in CDB, it will be 4. So let's say if one of the services is deleted, you can delete the config that the service created by itself alone, because the dependency is only to this particular service. But the config that is shared between multiple services shouldn't be deleted. And that's taken care of by this reference counting and back pointers. So whenever a service runs and creates something on the CDB, we have attributes called reference counts and back pointers that tells you how many services are using this node or using this sharing this resource. And only when that reference counter is 0, we can delete it. So this makes sure that when you delete some service, config that is depended on by other services is not deleted. And then we have this diff. It's a simple diff program in Linux, or that is used in version controls like Git or something. It's basically the same algorithm that is used to compute diffs in NSO as well. This is also a very nifty thing to be useful, because since it's transactional, and if the transaction is successful, we can store, or we can have what steps are necessary to go from one state to another state. And in the diff algorithm, the problem is to calculate the shortest edit script to go from one sequence to another. So if you model the configuration as a long list of strings, you can compute the difference, or you can compute the set of steps needed to go from one config to another config. If you can do it in the shortest possible way, it will be very useful to get your system from one state to another state. And then we come to
does this include? I think this doesn't help. So does this include semantics? So you're having a long ACL,
Mm-hmm.
and well, maybe you can go and do further ACL aggregation if you're just adding a couple of additional entries. Would that be part of that?
It's not part of NSO. Yeah, it's not part of NSO because NSO doesn't understand the meaning of the config. For NSO, it's just data from the model. So NSO cannot determine that you're deleting the whole ACL and adding only 2 more. So instead of removing all the ACL lines one by one, you can delete the whole ACL entry and then add only 2 more. Not in NSO, but you can do it in the NEDs, and NEDs do have that capability nowadays, especially in devices like Cisco iOS devices, for example. We have a capability to say that now I'm deleting the whole ACL and adding only one or 2 more entries instead of, the diff that NSO gives to the NED will be a long list of removing all each ACL entry and then finally adding only 1 more. But then the NED can know that this case is deleting the whole ACL and adding only 1. That's much faster. So you can do that optimization in the NED, but not in NSO. Yeah. And Yang is the data modeling language that we use in NSO to model basically everything. So it's specified in these RFCs. This is Yang 1.0 and 7950 is Yang 1.1. It's the new version of the Yang specification. So Yang is tied together with netconf. So netconf is the management protocol for managing the devices, and Yang is the data modeling language that's used to model the device behavior. So Yang can be used to model the config data or the state data and even alarms and notifications that the device is capable of using. And NSO itself is modeled in Yang, so that's also a power of NSO, that it's completely model driven. So if you know the Yang model of a particular system, you know its whole capability, what it can do, and what are its capabilities. So NSO comes with all the models that are internally used in its release. So if you can go to the NSO release and look at the Yang models, you can understand a lot about what's going on. For example, the NSO's own device model is there in the release, service models, packages. So you can just look at the Yang models from NSO to know what are the actions available, what are the RPCs, and what are the capabilities in general, and config data, and so on. And there's also a lot of documentation available in the Yang models usually. And towards the devices, most vendors have their own set of devices for set of Yang models for devices that they expose nowadays. There are also standard Yang models for IETF interfaces or IETF IP and so on. So there are even standard service models like standard L3 VPN model or standard L2 VPN model that are coming up from IETF these days. So that's the power of Yang. So the power is that once you know the model, you know the whole capability of that device, or the capability in terms of netconf mostly, but also in terms of other systems usually. So once you know the model, you know the whole behavior or capability of the device. And now we come to the central algorithm that I talked about, called FastMap. It's the algorithm that NSO uses to map a service config to a device config and manage the services also. So the power or the promise of NSO that's very attractive is that you only need to specify the create part of the service. So in your service model or in your service code, you specify how to translate a service config to a device config when the service is not existing in the network. So let's say you are bringing up a VPN. So you model some parameters in the service model, and then in your implementation, you assume that the components of the VPN are not in place in your network, and you just tell the service what to do, assuming that the service is not there in the network. So bring this interface up and tie these together, and whatever is needed to bring the service up from nothing. And then NSO takes care of the updating and deleting part by itself. So that's the big promise that NSO provides you, that you only need to provide or you only need to tell NSO how to create the service. And once it's in place, you can update the service and you can delete the service, and the code for that is handled automatically. So let's see how that works actually. So this is the service create case. So in the create case, you don't have the service actually provisioned in the network, and you get the service parameters from the northbound system, like an order management system or an OSS. And you use the NSO's APIs, like the create callback, to map that into the corresponding changes to the device models. And what NSO does is, as I mentioned, it has the ability to calculate the minimum diff necessary to take a device from a given config to another config. So once you have the diff from A to B, it's also very easy to have a diff from B to A. So we calculate the reverse diff, that is what is needed to get the system back to the previous state, and then we store that reverse diff in CDB. So now you have so right now you have the service parameters and the way to get the system to the state where the service was not there. And now you can calculate the changes based on your service code or based on templates, and then NSO can push those changes to the devices. So this is what is the create case. It's the only difference between directly going to the devices is that you store the reverse diff in CDB. And then when you want to delete the service, how does that work? So you have the reverse diff in the CDB, and when you want to delete the service, you just apply the reverse diff in memory and then calculate the diff needed to bring the device to this state, because you have the device config also in CDB. So once you sync from the devices, you have the device config in CDB, and you also have the reverse diff for this particular service. So if you apply the reverse diff, you will get the new config that the device has to be in, and then you can calculate the diff between that and the current config in the device. And then you can send that diff to the devices. So note that you don't need the create callback here. So you don't need your service code to run for the deletion case, and you also don't have to provide any parameters. You only have to say delete this service, and then NSO takes care of the deletion by itself fully without involvement of your service code. And probably the most complicated case is the update case. So update case means that you get some parameters from the northbound system, but it's not for a creation of a new service. It's for modifying an existing service. Maybe you change the bandwidth here or QoS or delete a parameter that's not relevant now. That's not deleting the whole service, but just modifying an existing service. So how that works is that when NSO gets the query to update the service, it again applies the reverse diff internally in memory. So now it has the config to go to the clean slate or to the first state where the service is not existent. It doesn't send anything to the devices now. These are all done in memory. So in memory, you apply the reverse diff to see what changes are needed to bring to the state before the service was created. And then you run the create callback with the new parameter now. So you have an updated parameter So you can run the create callback with this new parameters, and now calculate the same diff, or now calculate the new diff to be sent to the devices, and store the reverse of that diff in place of the old reverse diff, and send it to the devices. So the important part is the reverse diff is stored here. You can also view what is being stored in the reverse diff from the CLI or programmatically. Any questions?
Thank you. You mentioned that the first reverse diff is done only on memory from NSO perspective.
Yeah.
And then it cleans, everything, and create a new service with all the new parameters. So,
yeah.
But what is actually sent to the devices?
Yeah, it's the minimal config necessary to have
just the additional configuration that is necessary.
Yeah.
Okay, got it.
Yeah.
So what happens when there's been change between applying the?
Sorry.
So when you've done the create and you've applied the service, and then you want to delete the service, what happens if there's been change that's happened in between the two, so that your reverse diff is no longer where you want to be? If that makes sense.
Yeah. So this one, you mean that when you apply this, the state of the network is not the same as when this diff was calculated. Right? Yeah. So that's a risk, but you have actions to check that the device is in sync with the CDB. So before deleting a service, if you check that the device is in sync with your CDB, then you are sure that the reverse diff is still valid.
But if I've applied another service, then the CDB would be updated with that new service.
Yeah.
But it would be different from the before state from this original reverse diff.
You mean that both services touch the same part of the tree? Or?
So I apply service 1,
and
I store the reverse diff for that.
Okay.
I then apply service 2.
Okay.
And now I want to remove service 1, but
Yeah.
leave service 2 there.
Yeah.
But the reverse diff I have was from there being no service applied and service 1. So that reverse diff doesn't know anything about service 2. And there may be some things that in service 2 that change is the same config that service 1 was changing. And I don't want to go back to my state before service 2.
That's what the reference counters and back pointers are used for. So when the reverse diff is applied, you see that this service touches something that the other service touches also. So I should not remove that. I should only decrement the reference counter, but not remove it from the tree. So, oh no. Yeah. So this is how the fastmap algorithm works basically, and there's another variation of this called reactive fastmap that is used for when you have dependencies on an external system. So like when you have some resource manager or an IP address allocator, for example, that you want to get an IP from, or from a DHCP server, you want to get an DHCP address first before proceeding with the service, for example. So in those cases, the algorithm is basically the same, but you run the overall fastmap loop multiple times. So the first time you run it, and you probably get the address, and then the address is written to an operational data, and some subscriber that is waiting for updates to a particular tree will look that you have got the address now and will trigger a redeploy of the service. And then you go into a new transaction and do the same thing again, and maybe if you have another dependency in your line, you wait for that dependency to complete and redeploy again. So the fastmap cycle is run multiple times in the same service. So that's called the reactive fastmap, and that's useful for if you have external dependencies in your service. And finally, we come to some NSO use cases, or how people are using NSO. And the first one is high availability. It's the quintessential reliability or high availability concern. NSO has a HA framework or HA API that it exposes. It doesn't have a fully managed HA framework by itself. There is no automatic leader election or automatic failovers based on any conditions. It's up to the user to configure that framework. NSO exposes an API to set a particular node as master or slave or none. And it's up to the user to have their own framework. I mean, we do have a package called tailfhcc that is a high availability controller, but the users are free to use their own frameworks if needed. And NSO just needs to be told when to be master or when to be slave. And the exact way that's done depends on the use case. So maybe you can have a package in NSO itself that says that this node is master now and communicates to the other node that you're slave now. Or you can use other frameworks, like I have had some customers using something called CoroSync and Pacemaker, because they have a whole HA system of their whole ecosystem, and not only NSO. So they have rules to change based on multiple parameters, like reachability of NSO or availability of BGP routes or whatever metric they have. So then you just need to tell Pacemaker when to make this NSO slave and when to make that NSO master, and so on. So this is the high availability. Yeah, right now tailfhcc offers switching based on VIP availability or virtual IP interface. You have two NSO instances, and you can have a virtual IP interface in both the instances with the same IP, and if one of them is not reachable, it will switch to the other one. So yeah.
What if replication is still in progress and the external system like Pacemaker doesn't know whether it's already finished or not? Will it just fail if we make the other node master that was previously a slave but replication hasn't been finished? Or there are any ways to figure out whether it's already finished or not, or it's still in progress?
So when a node becomes a master, it will there is a field called transaction ID that is stored in NSO. It's the system-wide transaction ID for the whole NSO. So whenever a replication is going on, whenever new transaction is arriving in the master, the slave will, the master will update the slave with the CDB config and oper data, and then once it's done, it will update the transaction ID. So if this replication is going on and you try to switch over, the other node will not become master until this synchronization is done. Basically.
So it's kind of a synchronous process.
Yeah.
And you need to wait until the new master eventually takes over.
No, if you...
For instance, when the replication is finished.
Yeah, and if you lose connection with the master, for example, and the Pacemaker framework decides that, okay, this node is not reachable now, so I have to go to that one. If the slave also cannot talk to the master for some time, and then NSO will just accept that when Pacemaker says you are now master, it will just accept it. But it might miss some transactions because of this loss in connectivity, but that's expected.
And when you talk about transactions, only CDB transaction, or like the whole system, for instance, applying configuration to the device and all that, is it involved into transaction, or it's only CDB transaction?
I think NSO doesn't differentiate between these two, and at least in a HA system, only the master can talk to devices. So the slave can only update its own CDB with the diff from the master. So the slave can only synchronize with the master, and it cannot talk to the devices directly.
Thanks.
Yeah.
How would NSO nodes recover from network splits? Like master is gone, you can't reach it, but it thinks it's a master, and one of the slaves take over and writes to
Yeah,
devices.
that's the thing, right? So NSO doesn't take over by itself, so it needs someone to tell who is master now.
Okay.
So it's your framework's responsibility to do that, I think.
How about if the device has the problem and still thinks the other node is master and notifies the old master? How
The
does
device
that-
has the, sorry?
Yeah, the problem was on the device that's
Okay.
controlled, and it sends notifications,
Okay,
telemetrics,
okay.
sends it to the old master because it missed it.
Yeah, so the easy use case is the virtual IP. So you have a virtual IP in both nodes, and if one of them is down, the other one is still reachable.
Fixed
So
network.
so the device doesn't know which NSO it's talking to. It just talks to the address, and the address will be up in one of the nodes, hopefully.
Thanks.
In the case of the CDB, right, like how multi-tenancy is, like a customer might have different customers, right? So how is that handled, like in a secured manner? So one customer doesn't want to see others.
Yeah, so access restrictions are based on NACM rules. So NACM stands for NetConf Access Control Management. There's a Yang model for that, and you can restrict based on a lot of things, like based on the username, or so this user can only access this tree, and this user can only execute these RPCs, or they can only execute these commands in the CLI. So you can restrict based on a lot of metrics in the NACM model. So yeah.
Thank you. You mentioned that we can use a certain kind of framework to help us with the
Yeah.
process to switch over. So, but in a very, I mean, without any framework, so those different boxes, I mean, the active and all the standbys, they can belong to different IP address ranges, I suppose. And is there any way to have any kind of load sharing between them? Because you mentioned that the standbys, they will only, they will not
Yeah,
talk
yeah.
to devices, right?
Yeah.
So does it make sense to have any kind of, is there any architecture that we can have with load sharing?
No, that's a difficult thing, because if you have load sharing, if you have two NSO instances, then their CDBs will be different. So if one request come to one NSO, the contents in that CDB will be different from the other one. So you have to constantly synchronize, and before taking on any new transaction, you have to make sure that whatever is in the other CDB is also in here. So we don't have load balancing capabilities. as of
Even
now.
they're sharing the same storage, for example?
How can they share the same storage?
I mean, those two different physical servers pointing to the same storage system. Just trying to think in a certain. Yeah.
Yeah, no, you can't use that, or you cannot use it in such a way. Um, yeah, I'll get to those things later, or right now maybe. So the other way that I mean, these are all kind of disjoint. So you can use clustering along with HA, and LSA along with clustering with HA, and so on. So clustering was the feature that was provided for scaling, in this case even load balancing as well. So here you have layers of NSO nodes. So in the top NSO node will talk to other NSO nodes and not the actual devices, and they will talk to the actual devices. But then you still have a network-wide view in the top NSO. So you just say that these NSOs down here are remote devices. So you treat them differently. So you don't talk to the devices directly yourself. You talk to the remote devices, or you talk to the remote NSOs, and they talk to the devices. But then the service packages and device models are common in both of them. Yeah. So this is one way of load balancing, I guess. Yeah.
That's just an architecture.
Yeah.
I understand.
But then the problem with this is if the device config gets very huge, I mean, FastMap needs the whole config to create diffs and calculate the ref counts and back pointers, right? So in the top node, you will not store the config of the whole network because you have the lower nodes to do that. So let's say that you have one node in top and two nodes in the bottom that each talk to like 5 devices each. So you'll have the first node in the lower layer have the config of those 5 nodes, and the next node in the lower layer have the config in these 5 nodes, because this NSO doesn't know about the devices in the other NSO's node, so there is no need to replicate devices across or replicate config across both the nodes. So what will happen is when you create a service in the top node, it has to first get the config of the devices from this lower NSO. So it will use, I mean, since it's both NSO, they talk via netconf, and it will have to first get the whole config for that relevant device from this NSO first. And then it has to calculate the reverse diff and the changes to send to the device and ref counts and so on. And then it has to send those diffs back to the other NSO, which will in turn talk to the devices. This works fine if the device config is very small or it's not very deeply nested, because otherwise getting the full config of a device via netconf takes some time. And if it involves multiple devices, it has to get all the config from all the devices before calculating the diffs and so on. So this is a very useful trick if you are not managing a huge number of devices, or if the configs in each of the devices is not huge.
What's the reason for doing that?
Sorry?
Why would you have multiple NSOs down the bottom with a single on the top? If that single one on the top is going to do all the work that would exist.
Yeah, because you, as I said, if you have huge configs, it will be, or not even huge configs, if you have a lot of devices, like tens of thousands of devices, it will be a problem to hold all that config in memory in only one node. Yeah, so basically. Yeah. So if the config is small, it's okay. So if the config is multiple millions of lines long, it will take a lot of time to see. But then this is.
If the config was small,
yeah.
Why do I need to have all the ones down the bottom? Why can't I just do all from a single?
Because the config of one device is small, but if you have thousands of devices, it will add up, right? So that's why you split it into multiple chunks.
I thought you said that it has to pull all of them together.
Yeah, but not everything. So let's say you have one NSO on top and two NSOs at the bottom, each with 5 devices each, and you have a new service at the top layer that only touches 2 of the devices here. So it only has to get the config from these 2 devices, not the entire config of all devices.
But if you wanted to deploy a service that touches all of the devices,
yeah, then this is not the correct architecture for you.
So what is the right answer?
Yeah. So that's the exact issue that the customers were facing, that people had a lot of devices that were also huge. And then the answer was this one, layered service architecture. There's another talk later today about scaling this. I think it's the next one right now in the main hall. So what happens here is you still split it into top and bottom services, or multiple layers even, but then you don't have the same model in the top and bottom layers. You adapt the model so that the top layer only knows about the lower NSO nodes, and it knows nothing about the devices at all. And the lower nodes, in turn, know about the devices underneath or the other NSO nodes. So there is some work required to have this working, because you have two different services now. So one is the customer-facing service, so to speak, which is in the upper layer that only talks to the lower layer NSO devices, NSO nodes. And then you have another service package in the lower nodes that talks to the actual devices. So then this whole config sharing is not a problem, because of course you lose something here because you don't have the whole network-wide picture from the top node alone. So if you want to examine exactly what's going on in each of the devices, you have to go to that particular NSO node which is talking to that device. Yeah. There are references to which NSO node holds which device, but it doesn't. The top NSO node doesn't care about the devices at all. So it only calculates the changes needed for the lower NSO node, and then that NSO node will calculate what is needed to be sent to the devices. Yeah. So yeah, that's it. These are what I think is some very basic building blocks of NSO. Any questions? Yeah.
Additional question about transactions. We are currently having a project when we configure different devices using NetConf protocol. As I understand, Cisco NSO doesn't really have any transactional model except the kind of custom rollback or something. So when certain changes are applied and something goes wrong, let's say that we've already went through 5 steps. We need to roll back each of the 5 steps step by step. No pun intended. So thing is, there is no real transaction because rollback can also fail. Like we can roll back 2 steps that you've done, but 3 remained unrolled back if the third one has failed.
Yeah.
Are there any plans to improve the situation, and any thoughts on this? Thank you.
If the devices are transactional, then it's no problem, right? Everything will be great. But the devices are not. So, I mean, as you say, of course, rollbacks can fail. But then those are very rare. And if it happens, we need to look at why exactly it failed, and we have to handle it in the nets. It's an ongoing process. And for example, a lot of devices have dependencies. So when you configure something, it's one way, but when you have to roll back, it's some other way. So you have to take those dependencies into account, and it's an ongoing process. Like when you find these issues, report them to the TAC, and they'll the net will be adapted to that particular use case. But then it's not very easy to handle it in a generic way, of course, because the devices themselves are not transactional. That's the thing, right? Yeah, commit queues. Commit queues are could help. Okay.
Okay, if you have any
Thank
more
you.
questions, you can catch Ram later, next 3 days. Thank you, Ram, for the nice presentation, and it's a small appreciation.
Thank you. Thank you.